Maximize vertical reuse, building a module to system verification environment with the UVM. 자, given the size of the complexity of modern SoCs and ASICs and SoC, coupled with their tight project schedules, it's implicated to build a complete system or a chip-level verification environment from scratch. Instead, in order to increase productivity, maximize the use of existing verification components seamlessly with the project has become one of the biggest opportunities to increase verification efficiency. In this paper, we present a test bench framework to maximize the vertical use within a project. The framework presented here has been proven on the ground up with development of 200 million gauge ASIC. In our framework, the system test bench is built in a hierarchical manner by recursively importing lower-level block or module test benches. From the lowest level to the highest level, all the test benches are designed to support plug-and-play integration, so the verification engineers can hook up the several lower test benches and turn them into a higher level test bench. The system test inherits the device configuration sequences, traffic generation sequences, checkers, and monitors from the imported module test benches without a duplication of effort. As a result, vertical reuse shortened the development time of the system test bench, improved the quality of the test bench code, and allow fast to bring up during the system integration. The introduction. Section 1, Introduction. Building system or chip-level test benches from the ground up is feasible, undertaking for devices up to several million gauge. However, test devices of the size 1 to 10 billion gauge, now from the subsystem of today's device with 100 million gauge or more. Thus, a new approach is required to achieve the productivity gain required in order to avoid applying the same scale factor 10 times to the number of verification engineers. Tackling devices of this magnitude, 100 million over 100 million gauge, must involve using the divide and conquer strategy. Divide the device into smaller subsystems, and then further divide the subsystems into even smaller modules or blocks to limit the scope of verification at each level. A module test bench is built to thoroughly verify each and every module feature. A subsystem test bench is built to verify the subsystem level features and the interaction among the modules within the subsystem. Finally, a system test bench is built to verify the interactions between the subsystems due to their schedule pressures, resources, and the budget limitations. It is not feasible to build every test bench from scratch. Therefore, it is always desirable to share and reuse code from one test bench to another in order to minimize the development effort and improve the quality of the test benches by using a proven code instead of duplicating some of the effort by developing new code. With the introduction of the UVM, the industry has standardized a common test bench architecture, which enables the easy use of the in-house or third-party verification IP and individual test bench components such as your generator and receivers, traffic and configuration sequences, protocol checkers and coverage models, scoreboard, and in the previous project, we had hoped that the UVM architecture would have helped us facilitate the module to system level reuse. However, we found the current UVM guidelines lacked the framework to support seamless plug-and-play integration from module test benches to the system bench. In the previous project, verification engineers attempted to reuse components such as sequences, checkers, and monitors from the model and the test benches in the system test bench directly. In the end, although this approach failed for the following reasons. 1. Code maintenance. The code in a module test benches is designed for module level test bench, tends to evolve over time a little consideration for impact in the system level test bench. As a result, system verification engineers waste a significant amount of time trying to integrate the new releases of the lower level test benches. 2. Debug was a challenge. The module, the subsystem RTL, often went through many changes during the project, gradually matures. The module and the subsystem level verification engineers addressed those changes in their test benches, but sometimes failed to communicate the necessary changes to the system verification engineers. As a result, the system verification engineers wasted a lot of time debugging failed test cases that turned to be unknown issues. Knowledge transfer. When the system verification engineers debugged the failed test cases, it was difficult to get quick support from system verification engineers since they were not familiar with the system test bench and they could not easily reproduce the failed scenario in the subsystem test bench. Thus, because of this reason, the reuse model broke down. The verification engineers tended to duplicate code from the lower level test bench or merely used it as a reference for a slightly different implementation at system level. The current device on which this paper is based is 4 times bigger than the previous project, with significantly more ground-up development. Therefore, we had to streamline our vertical reuse strategy to maximize the time and effort spent by addressing the problems we had encountered in the past. Our goal is to create a test framework that maximizes the vertical reuse, thus achieving the significant productivity gain. The system level test bench can import the subsystem level and the module level test benches directly and reuse all their individual components. Changes in lower level test benches propagated automatically to the system level test bench. The system level test bench can export each configuration to the lower level test benches, which allows the lower level verification engineers recreate and debug failed test scenarios. The test bench framework supports plug-and-play integration, so the system verification engineers can focus on testing system-level issues without being overloaded by mundane operation details of the low-level test benches. So we surveyed the existing papers and articles on a vertical use to see what we can learn from other experiences. In blah blah blah. In one, Frehilichi proposed a reusing scheme that supports turning an active agent into a passive agent and synchronizing traffic generated based on the ERM. In reference to, the author proposed a module-to-system reuse topology based on a scoreboard chaining with the internal monitors to provide up some concern regarding modules to the system reuse, suggesting that the features in the module level environment is a superset of the features in the system level environment. Thus, the system test bench has to select wisely what to import from lower level test benches. In reference 4, the Donofrio outlined the reusable verification environment using multiple layers of the highly configurable component with the UVM. The scheme is similar to the system UVC architecture upon which we based our test bench framework. So our goal is simply to design a solution to maximize the vertical reuse within a project. We applied the lessons learned from the previous project and addressed the questions raised in the previous paragraph to design our new test bench framework, which is implemented based on the latest version of the UVM verification methodology. During the development of our vertically used framework, we discovered some limitations and scalability issues of the existing UVM framework. In order to overcome those limitations, we came up with the 3 enhancements to existing UVM framework to allow seamless integration of module test benches into the system test bench. The paper is organized as follows. In section 2, we introduced the existing UVM framework for modules to systemly use. In section 3, we present our enhancement to the UVM framework in detail. In section 4, we will summarize the benefits of the vertically use and provide some benchmarking, result, and outcome from our project. In section 5, we outline the challenges of vertically use that we encountered during the project and recommended improvement from the lessons learned. In the last section, we will briefly investigate the feasibility of porting our vertically used framework from UVM E to UVM system verilog. Just section 2, the system UVC architecture. Our test bench framework is based on the UVM E system UVC architecture outlined in the UVM E user guide. The system UVC architecture is a solid foundation for vertically use, in that it outlines vertically used topology and discusses how to configure low-level UVCs that are promoted into higher-level UVCs. It also has a useful guideline on how to implement and maintain the reuse codes in the lower-level UVC. This section will briefly introduce the concept of the vertically use. Please refer to the 7 to implementation details. The figure 1 shows a module test bench. The terms module test bench and a system test bench are relative. A module UVC is a lower-level UVC to a system-level UVC, which itself may also be a module UVC relative to the higher-level system UVC. The device level or the system test bench can be built in hierarchically by importing one or more layers of the module UVC. The module test bench is very similar to a typical UVM test bench with the following exception. The master virtual sequence driver and a register sequence driver is used outside of the module UVC, since in each verification environment, there is always one and only one master sequence to control the test flow. The master virtual sequence driver and register sequence driver are linked to the Testflow virtual sequence inside the module UVC using pointers. The stimulus generation is separated into multiple layers. The interface layer directly drives the digital signals. The protocol layer deals with the transaction level processing. And the payload generation layer creates the client payload. Each layer is connected by the TLM port. So the system UVC can tap into a layer into the protocol stack without changing the structure of the imported module UVC. The receiving the traffic checker and the monitors are also unstructured in a similar manner using a TLM port. In addition to the reused protocol checkers, VIP UVC and the module UVC has its own checkers and a scoreboard that are accessible by the system UVC. Figure 2 shows a system UVC that imports 2 modules. UVCs as a simplified example. There is no limitation to the number of modules UVC in a system UVC and the depth of the module UVC levels in the actual implementation. Our system test bench UVC is composed to a 10 subsystem UVCs and some subsystem UVCs have 3 to 4 modules UVC, thus have a total depth of 3. In the system test bench, the master virtual sequencer driver is linked to the virtual sequence of the system UVC, which in turn links to the virtual sequence of the imported module UVCs. The module uses signal port interfaces that are connected to the internal RTL signals are disabled by the system UVC. After traffic generation in a module UVC, it depends on another module UVC, such as one protocol being encapsulated in another protocol. The system UVC will connect the TLM port of association protocol layers in the related module UVCs. The module monitors and the scoreboard are chained up to perform end-to-end checking. For interface UVC found in the middle of the DUT, they are often disabled, but can be enabled as a passive agent. This allows the module level of checkers and the scoreboard to perform hop-by-hop checking, and which helps verification engineer to pinpoint the failure when debugging a failed system test case. Section 3. Enhancement to the system UVC architecture. Although the UVM architecture is designed to address many concerns in the verification reuse, we found its structures is not flexible and sometimes inconvenient to implement. Therefore, we proposed 3 enhancements to system UVC built-in extended method. The source port is and channel ID pair is used as the key to look up the destination port ID and channel ID from the routing table. There could be, I think there's some, using okay. Right. Okay, the system UVC architecture to address the problems. The TLM port router. The system UVM architecture relies on the TLM port binding mechanism to transport the sequence, items, and transitional code. So among the module UVC, and however there are some limitations, and the UVM TLM port default binding mechanisms, such as 1. TLM's transport port only supports one-to-one binding. 2. The TLM analysis port supports one-to-many bindings. But the transition code is always broadcast to all input TLM ports. And 3. When the input and output TLM ports are bound, the building is static. The limitation imposes a rigidity restriction in how the system UVC import and connect to the lower-level module UVC. In order to support the flexible module UVC configuration during the simulation, we developed a TLM port router to overcome the above limitation. The system UVC connect to the module UVC TLM port to the TLM port router instead of connecting up to the port directly. With the help of the TLM port router, the UVM UVC can easily change the routing table to the redirect, or reconfiguring the port connection during the simulation. The TLM port router is implemented using an E-template, which allows the reuse of the same piece of code on the various data types. The router implements a table-based generic routing algorithms using the port ID and the channel ID. The port ID is determined by the TLM port interface. The transaction comes in. The channel is fetched from within the transaction using a built extended method. Built extended method. The source port ID and channel ID use pair is used as a key to look up the destination. Look up the destination port and the channel ID from the lot table. There could be more than one station for each tier source, If the destination supports the multicasting, the router will be updated to transition with the new channel ID and duplicate the transition in the case of the multicasting, and then send them to the corresponding destination port. The routing table lookup algorithm is implemented using an E key list to speed up the search time. The following is an example of the header definition of a TLM analysis, both a router and the routing table. The B. The common UVC configuration control. When the module UVC is used to the module level testbench environment, the TL ports between the all internal UVCs, the monitors and scoreboards are connected and bound. However, when the ports in the module UVC are bound, and the system UVC cannot bind the TLM port without affecting the functionality of the module UVC. One way to solve this problem is to leave out the binding constraint from the reuse portion of the module UVC algorithms. If it's altogether, the system module has been referenced to the reference code in the module testbench to connect the internal component of the UVC from the scratch. This solution is not productive since the system verification engineer often lack of understanding the internal connection of the module UVC. Since the system UVC often preserves most of the connections inside the UVC, a better solution is to let the system UVCs disconnect the blending of unwanted connections while keeping the rest intact. Each module UVC has a common configuration control table. It stores all the binding options for each UVC and component inside the module UVC. The table is organized using the RTL port as the first index of and the number of protocol stack layers at the port as the second index. The table keeps track of whether the UVC is enabled and disabled, whether the agent is active and passive, whether the TLM port binding is connected to the left or connected or left open. The module UVC has to obey the configuration control when generating the UVC instances or hooking up the TLM ports and the connected ports phase. The table is implemented using a keyed list to provide a quick access to the configuration control information. The following is an example of the common configuration control table. C. Common test flow as a virtual sequence. The virtual sequence of each module UVC runs the configuration sequences that are traffic generation sequences of the module UVC. The UVC system UVC needs a mechanism to coordinate and synchronize the behavior of the imported module UVCs. In our vertical reuse framework, all module UVC virtual sequences inherit a common test flow structure, which defines the empty time consuming method TCM, known as test flow phases. Each test flow phase is designated to carry out a specific function in a simulation. The module level verification engineer extends the test flow phases and fills into the required action for a module level testing. As we decided not to use the UVM test flow because it is too complicated, requires too much time, much setup, and prone to the human error. We implemented a simple test flow with a single entry point at the highest level test bench. The system UVC virtual sequence will execute all the test flow phases from the all imported module UVC in rock step. We defined three different kinds of test flow phases, which represent three different ways to synchronize the module UVCs and the system UVC. An execution in the serial in which test flow phase of the one module UVC is executed to completion before then moving to the same test flow phase in another module UVC. For example, using this test phase time will ensure two modules UVCs would not interleave their registered accesses. Execution is parallel, in which the same flow phases of the module, all the module UVC are launched in the parallel, and the system UVC test flow phase will not move forward to the next test flow phase until all the module UVC test flow phases are completed. For example, the tested flow cannot proceed until all modules come out from the reset. 3. The execution in parallel with the fire and forget, in which the same test flow phases or the module UVCs are launched in parallel, but the system C UVC test flow phase moves on to the next test flow phase once all the test flow phases in the module UVCs are launched. For example, all modules start their traffic sequences with no need to the coordination among the sequences. The system verification engineer can use the three basic test flow phase kinds to build up a common test flow that fits the operation of the device with a lot of flexibility. Figure 3 shows an example of the test flow phases used in our project. Initialize the test bench environment. 2. Toggle the reset pins of the device. 3. Wait until the device is ready for offsetting the register access. 4. Configuring the test bench with the procedure code. 5. Configure the device with a register or backdoor access. 6. Start traffic generation. And this is the figure 3 common test flow example. Okay, 6. Start traffic generation. 7. Wait for the device stabilized. 8. Empty method 2 following test case to create a stimulus. 9. Any simulation trace free if timeout period expires. 10. Catch system errors and abort the simulation. 11. Initiated the termination of the traffic sequences. 12. Wait for the traffic sequences to be terminated. 13. Wait for the clean traffic to flush out the device pipeline. 14. Check the device status. 15. The check time, execution time consuming most simulation check. Section 4. Benefit and result. The most significant benefit of the vertical reuse in a verification is the engineering time saved. In general, the development effort and the number of bugs in the test bench is proportional to the number of lines of the code test bench. The bigger test bench, the more time spent in the writing the test bench and catching the test bench bugs instead of catching the other bugs. In the table, we compare the size of the test bench in the current project against the previous project, which gave us a good approximation of the productivity gain. With the help of our vertical use framework, we were able to verify more gates with fewer lines of code. If we measure the code density, how many gates are verified by one line of code, and we achieved a very impressive 4 times productivity increase in the current project. Table 1. Vertical reuse statistics. Okay, the vertical reuse framework also saves us the significant time in the system integration, thus enabling us to, along with the method, to meet our tight tape-out schedule. In the previous project, it took 2 to 3 months to build the system-level test bench. In addition, endless hours were spent in maintaining the system test bench code to keep up with all the wanted and unwanted changes in the new module-level test bench releases. In this project, since the module-level test bench is designed to supporting the plug-and-play integration, on average it takes 2 to 3 days to get one subsystem up and running. The completed system-level test bench was fully integrated in less than a month. The verification engineer is able to easily populate the new code from the module test bench, and in most cases it will be work and the system level test bench unchanged. At the previous project, system level verification engineers struggled greatly to understand how to stitch all the pieces of the reuse codes from the lower level test bench together. In this project, it is much easier to develop system level test case. The verification engineers can simply import two subsystem level test cases and constrain them to generate a coherent traffic mode and finish a system level test case in less than 20 lines of code. Another benefit of our politically used framework is the stepping up to the system level debugging on turnaround time. In the previous project, when a system verification engineer encountered a system level bug, it was harder to pull in a system level verification engineers to debug the problems, since the subsystem verification engineers are not familiar with the system level test bench. In this project, we found a bug. We can enable the internal modeler of the module UVCs and a pre-passive mode, and it works. Provide us the same detailed debug information as in the module level test bench. The subsystem test verification engineers do not need any ramp up the time to help us to analyze the problems, because they are essentially working with their own test bench. The 5 challenges. We have learned some lessons and are politically used from this project. The first challenge is the revision control of the reuse VIPs used across multiple module test benches. Usually, more than one module UVC reuses the same VIP. If the two modules UVCs require different revisions of the same VIP, there will be a revision conflict in a UVC system UVC level. We addressed this problem in several ways. 1. Freeze the development of the reuse IP early in the project. 2. If the changes to the VIP are unavoidable, the new revision should be backward compatible with the old revisions. And 3. If the backward compatibility cannot be maintained, the verification engineers who is in charge of the system UVC integration should coordinate with the module level verification engineers to update the reuse VIP revision used in all module UVCs at the same time. The second challenge was the poor quality code from the module UVCs impaired the system level test bench performance. Junior verification engineers working in the module UVC sometimes implement inefficient code that consumes a lot of CPU cycles or causes memory leaks. In module level testing, the simulation footprint is small and the simulation time is short, hence the problem of the bad code never surfaces. The system UVC inherits the code of all module UVCs, including the bad code. In systems level environment, there are multiple instances of the module UVC, and the system simulation runs for a much longer time. The bad code quickly delays the simulation performance, and sometimes can even causes the simulation to crash. As a guideline, the UVC verification engineers should run a profiling in their code to identify and fix any bad code. Experienced verification engineers should conduct a code review with the junior verification engineers to catch any potential problems early in the development cycle. For example, we had a 30% simulation performance improvement just by rewriting those number lines of the bad code. Chapter 6, Future Development. The vertical reuse framework outlined in this paper is implementing a UVM. Since UVM system verilogging is also the other popular verification methodology in the industry, we conducted a brief feasibility study to investigate the possibility of the porting of a vertical reuse framework to SV. One of the major obstacles is that SV does not support the aspect of oriented programming (AOP), and many of the modules to system UVC features are implemented using AOP techniques. According to the reference 9, the system value can mimic AOP techniques using the design patterns, but the code implemented using design patterns require considerably more lines code to implement using more complicated software structures than the code implemented using the native AOP language construct. The system UVC that import the instantiated module UVMs is an application of the typical OOP programming technique, supported by both an ENSV. However, in the UVME system UVC architecture, system UVC uses the when subtypes to override the default settings in the module UVCs. It is possible to implement the setting the control using system value by explicitly exporting the configuration parameters of the module UVC. However, for reasons mentioned above, the using the design patterns is less convenient as it requires more upfront planning. It also requires access to the module UVC as source code just in the case the verification engineers has to be modified module UVC classes. Both the TLM port router and common configuration controller implemented the lookup the table using the e-keyed list, which is similar to the associative array in USB. The TLM port router uses a template to reuse the same piece of code on different data types, which is similar to the parameterized types of the SSV module. The biggest problem porting the framework to the SV is the common Testflow phases that are used in many AOP techniques. It would require a lot of work to replace the current AOP implementation of Testflow phases using the callback functions and class factories. That it may not be practical, but it is possible, at least in theory. The section 7 is conclusion. In this paper, the authors successfully implemented a module tool system vertically use a strategy to verify the 200 million gate device. There are many advantages of the vertically use, including the higher productivity, fewer bugs, and a higher quality in the test bench code, and a faster RTL debugging turnaround time. Our benefits contribute to both lowering the development cost and shortening the project schedule. There is a 4 times productivity improvement when measuring productivity issue code density. Okay, thank you for your time. Today I read this paper. The maximize vertical use building module to system verification environment with UVME. Thank you for your time again, and see you next time.